Yes, sir. So it seems I am ready. And
Yes, sir.
yes, sir. Yes, sir. Yes, Madan Lal ji. Yes. Thank you
Yes.
so much. Thank you so much.
Let's we start, sir.
Yes, if you like.
Yes, sir. Sure. So, in this fourth session, Dr. D.S. Kulshreshtha is with us for the new lecture, String Theory, a theory of quantum gravity on one-dimensional objects. Hand over to you, sir.
Okay. Thank you, Dr. Madan Lal ji. Thank you so much.
Thank you, sir.
Thank you so much for your very kind introduction, for your very kind words. And now, once again, we all of us are together, and I like to extend my very sincere thanks to all the participants and the audience in the very first place. And then I, of course, also am very grateful to the organizers, all of you, Madan Lal ji, Dibya ji, and Professor Sanjay Pant ji. Everything takes time and energy to organize and to do and to sit on the lectures and communicate with each other. So, you see, I'm very happy about it, and I'm very happy that people, I mean, the kind of questions that I'm getting encourages me uh, to speak further. Right? So, actually, the main purpose of my talk would be to generate enthusiasm among the younger generation. You see, that is the main purpose. As a teacher, I'm somehow people, my students tell me, sir, you are a, they love me. So uh, I'm not so much of a researcher. I'm more of a teacher, as you might notice in conversation with me. I want to be a good teacher only, and of course for that I have to be a student also, a good student. So I try to be good at both the things. Okay, so in our next talk, this is again looking for a theory of quantum gravity. So here we talk about superstring theory and superstring theory. We will go into the details of these. But before that, as a part of continuation of my earlier talk, and the topics are of course the common, and so the motivations and ideas are quite common. They need to be developed further. And before that, so you see, when we talk about, we need to realize two things: that field theory or quantum field theory is a very fundamental subject, and general relativity gravity theory is also a very fundamental subject. But as I said, that this is a kind of generalization of the field theory to curved space-time manifold. So now let me emphasize that, you see, if you generalize quantum mechanics to three space one time dimensions, okay, then, or you go back from conventional field theory to so quantum mechanics is a kind of field theory in just zero space and one time dimension. So that is quantum mechanics. Okay, so now, and if you write it in general in curved space time, you get gravity theory. You get yes, gravity theory. And if you introduce supersymmetry into the theory, you get supersymmetric field theory, which is a summarized in supersymmetric standard model. If you introduce further, you have generalized it further, so supergravity theory and so on. Now we make one more generalization, then that would be string theory or superstring theory. So it's all, these are different manifestations of the same idea, same idea, which is field theory, which goes from one end to the other end. Okay, and here, as we talk about gravity also and the quantum theory also, the fundamental idea of both the theories, I feel I have the temptation of telling you some very important the so-called things that are being talked about in the among the scientists. So let me start with this guy called Carl Sagan. He was born around 1934, and he lived for about 62 years. But he very, very celebrated American planetary scientist who wrote many, many papers and many, many books. One of the very celebrated book is Cosmos, by the title Cosmos. And he had the courage or to, you see, most of the scientists that I meet, I'm talking of people outside our country, they all believe and respect our ancient Indian thought. I don't want to associate any religion to any of these things, but ancient Indian thought, ancient Indian literature. And in that, Carl Sagan appreciates. He explicitly says there were, yesterday I looked into Google to verify things that people were so curious. Did he really say this? Yes, he said this. So in one of the Quora, the expert says yes, he did say it. So he said that this ancient Hindu thought or the ancient Indian thought, let me put it more general, is dedicated to the idea that cosmos indeed go through an immense infinite series of deaths and rebirths. This is one thing he said, which is very important. And he also said that in the ancient Indian thought, we talk about the time scales that are somehow consistent with the modern cosmological scientific time scales. For example, as I said, the universe was born 13.7 billion years ago. Now, we have our ordinary day and night. All of us feel it, what it is. And then our ancient Indian thought also talks about the time scales of Brahma, the creator. And so, one day and night of Brahma would then, in the ancient Indian thought, would correspond to something like half of the time when the Big Bang took place. So let us say 7 to 8 billion years or so. One day and night of Brahma, you see, and compare this. So they are cosmological time scales. Ancient Indian thought, the Rishi Munis, the scholars, we are now trying to do these things. We are also in the same category, but they were very celebrated names. So they did also, they were aware of these cosmological modern, the concepts that are consistent till today with the modern scientific cosmological skills. Now, this reminds me of, I like to say a few words. Please take it only as a part of the ancient Indian thought, okay, and not as a part of any religion. So I like to tell a few things from Bhagavad Gita, my favorite book, one of my favorite books. Krishna says, सर्वभूतानि कौन्तेय प्रकृतिं यान्ति मामिकाम् कल्पक्षये पुनस्तानि कल्पादौ विसृजाम्यहम्, which translates to, he says, Arjun, all these let me explain it in Hindi. कल्पों के प्रारंभ में मैं सब भूत प्राणियों की रचना करता हूँ और कल्पों के अंत में वो पुनः मुझे ही प्राप्त होते हैं. सो कल्पों इज ए प्लूरल वर्ड फॉर कल्प. सो he refers to multiverse, not only just one universe. This is one important concept. And then he says, so this will have several interpretations. I would also make a interpretation of this as a path integral, which is a transition amplitude from vacuum to vacuum. You see, we have to know scientific things in consistency with the modern scientific thought. So you take the time evolution operator, which evolves a quantum state from time t1 to t2. You take its matrix element between some initial and final time and take square of the absolute modulus value of this. This is a transition amplitude. This in particular has a name called path integral. So these things were developed by the legendary physicists Dirac and Feynman and so on. So this also, the sloka that I mentioned also explains the path integral, which is the vacuum to vacuum. One vacuum, first vacuum refers to the time t going to minus infinity. Look at the standard textbooks on quantum field theory. Time t going to minus infinity is the initial time, and time t going to plus infinity is the final time. Look at Bjorken and Drell, the celebrated 2 volumes on field theory. He talks about it very clearly. Then he says, Prakritim swam vastabhya visrajami punah punah bhutgram memam kratsan vasam prakatir vasat. He says that these things, I create these things, as I mentioned in the first one, according to their pre-assigned characteristics. Now, here I would like to remind my younger friends, please do look into quantum mechanics. In particular, my favorite book is Modern Quantum Mechanics by J.J. Sakurai, also Advanced Quantum Mechanics by J.J. Sakurai. Modern quantum mechanics is still simpler, which we teach in the classroom. And look at one-dimensional harmonic oscillator. What you do is, you take a linear combination of x and p and construct the creation and annihilation operators, A and A dagger, as they are denoted in this book. You can call them by any name. So, now, if you apply this, the vacuum state, in the vacuum state, I would tell you a little bit later, is also defined in Bhagavad Gita. I may not read the sloka here, but it defined in chapter 9. Chapter 9, please do look at the first few slokas, and you can look into the translation into your own personal mother tongue, whatever. We have scholars all around India. They have done it. So many of these concepts. And so here, now if I have and these annihilation creation operators, if I apply them to the vacuum state, let me say a creation operator to a vacuum state, I will create a 1 particle state. If I apply it to a n particle state, I will create a n plus 1 particle state. What is this? It's not, particle is not getting created. The eigenvalue of the quantum state increases by 1 quantum unit of energy h cross omega. But if I have, for example, field theory, a QED theory, quantum electrodynamics, I have an electron, positron, photon system. I have to write Fock space decomposition for each one of them, just as I did. That x could be a linear sum of A and A dagger, px could be a linear sum of A and A dagger. Here, all these creation and annihilation operators be, if I have in supergravity theory too many particles, particle content is much larger, then each one you can expand as a field. You can write a field expansion, Fock space decomposition. Fock space is when the number operator is diagonal, okay, capital N. So creation operator A dagger, annihilation operator A, and the product of the two A dagger A is Vishnu, the preserver. This, when applied to a n particle state, it does not change. It remains a n particle state. The eigenvalue does not increase or decrease by any amount. But if you apply a creation operator called Brahma, then your eigenvalue decreases by 1. If you apply Shiva, the destroyer, the eigenvalue goes by 1. And let me tell you, it's not my personal language. It's the language you can find in standard textbooks on quantum mechanics and quantum field theory. But I have met these people John Bell, and many celebrated physicists who like this terminology, because this is exactly. So now if I apply it to a vacuum state, for example, three creation operators, one corresponding to electron, one to photon, one to positron, then I would have a three particle state corresponding to one electron, one positron, one photon. This is what is written in this. This is what this Bhagavad Gita tells us in this. If we understand physics on the one hand and these thoughts on the other hand, you can find out a perfect analogy. See what happened, just to tell you a small story. On this day when our Prime Minister returned back from South Africa and Greece to India, he went straight away after the moon landing. He went straight away to Bangalore and talked to the ISRO scientists, the scientists like you people, to talk to them. And he made a so-called Ahvan. He said, Gyan, Vigyan, Prachin Gyan, Naya Vigyan, Naya Anusandhan. That is what he said. And then I immediately got some WhatsApp message and then the phone from DD News. सर आज शाम को आप प्लीज़ ज़रूर आ जाइए, मना मत करिए, हम आपके लिए गाड़ी भेज रहे हैं टाइम पर. आई सेड ओके, एंड व्हाट एम आई सपोज टू डू देयर. नहीं सर, मोदी जी ने जो अभी बोला है, यू हैव टू कमेंट ऑन दैट. आई सेड ओके, आई कम एंड आई डू दिस जॉब. देन आई सेड दिस slokas and explained them what Modi ji meant. So our ancient thought and ancient literature, we should not simply abandon them. If a Western person tells us this is this, then we, yeah, okay, great. But we should have self-confidence. Our people are full of brains and literature. A lot of these things, they do exist in our literature. We need to realize them. You see, in this is probably also in chapter 9, sloka 9, he says, Nachamam tani karmani nibandhanti dhananjaya. Krishna says, hey Arjun, none of these, ये जो कर्म है जो मैंने, I just now told you that if you apply three different kinds of creation operators to the n particle state, you increase it to n plus 3 particle state, one corresponding to those three of them. But he says, नचमाम तानी कर्माणी, ये सब मुझे नहीं बांधते हैं, मैं इन सब से इनवेरिएंट रहता हूँ. आई रिमेन, आई एम नॉट. So this is a dagger into A, that is Vishnu. So he says, if you apply a dagger A to any quantum state, nothing will happen to the quantum state. It would stay just as it is. So with these words, and telling you please look into some of these things. I would explain to you. I only want to make a reference to what Modi ji said, but this the Bhagavad Gita says somewhere in, also chapter 9, 01 and 02 slokas. He says only birds, Jnanam Vijnana Sahitam. In the next sloka he says, Raja Vidya Raja Guhyam. What is this that we are going to talk here? We are talking here. This is the quantum field theory. This is Raja Vidya Raja Guhyam. This is ये ज्ञान विज्ञान सहित सब भाषा, सब विद्याओं का राजा, सब हिडन लिटरेचर का राजा. That is this quantum field theory. You can go to quantum mechanics, you can go to field theory in one space, one time, two space, one time, or whatever dimensions you like. You can go all the way up to supergravity. You can now go to supergravity. So this is, I only want to tell, to motivate my younger generation, please, with an open mind, please do look at many of our ancient olden things, and you find lot of these rich concepts somewhere written in our in my another most favorite book is Ramcharitmanas, and I actually my Hindi used to be very good. So from there, if you permit me, I read a few lines. That there is a last chapter called Uttarkand, and there is a dialogue between Kakabasundi and Garud. You have to think of the concept. I personally have spent my lifetime only thinking of the concepts, attacking the concepts, trying to understand them without going into their other aspects. So he says that मोह बिलो की राम मुसुकाही बेहसत तुरत गयो मुख माही. उन्होंने मुझे देखकर उनको हंसी आई तो मैंने देखा कि मैं उनके मुख में चला गया. नाउ व्हाट हैपन्स, उदर माज सुनु अंडज राया देखे बहु ब्रह्मांड निगाया. उनके पेट के अंदर मैंने बहुत सारे ब्रह्मांड देखे. आई एम टेलिंग ओनली द कॉन्सेप्ट्स. अति विचित्रत हैं लोक अनेका रचना अधिक एकते एका. आई लीव द अदर लाइन्स without reading them, but again he says lok lok pratibhinna vidhata. Every system has its own creator. Bhinna Vishnu Shiva Manu Disitrata. They have different creation operators, different annihilation operators, different preservation operators. So I would not go further into that, but perhaps the last line which I would like to quote, the coming to the time scales of relativity. उभय घरी मह मैं सब देखा. दो पल के अंदर मैंने ये सब देख लिया. भयउ भ्रमित मनमोह विशेखा. I apologize to all those who may not have been able to understand my this thing, but I have no English interpretation of this in my mind, and we also don't have a time to go into all those. So this was just to motivate you little bit further on. After all, you see, leaders, they do matter. If I as your teacher tell you a few things, you might think, after all, what DSK said might be sensible. Let us think about it. Let us look at it. So I believe I am talking sensible things even in my earlier talk and even in this talk. Now let us go. So in our what I have told you is that there are two different ways to include gravity into our understanding of quantum field theory. One of them we already discussed, and it was the supergravity theory, where we stayed all through with zero-dimensional particles and fields. We were able to successfully introduce gravity into the theory. For that aim, the price that we paid may be the beneficial, that we introduced more symmetries into the theory. We introduced supersymmetry. Okay, we made we made the gauge symmetry to be local symmetry. So, and then we increased the number of supersymmetries. And this really helps us arrive at what our eventually aim is, or eventually aim was. This was our eventual aim, to construct a theory of quantum gravity which might explain many things beyond our conventional things. And this might include gravity into our fold, which we wanted to do, and this might lead us to a theory of quantum gravity. So supergravity is one of the candidate theories of quantum gravity. Now let us go to talk about another candidate theory of quantum gravity, and this is going to be string theory. And if we include fermions also, so it can be bosonic string theory, as well as if we also include fermions. You see, after all this matter around us, we all are made up of these electrons, protons, and so on. This is matter. So matter particles, these are around us, and they are fermionic. Okay, 6 quarks, 6 leptons, they are all fermionic. Okay, with spin 1/2. So we cannot live without fermions. So if you extend bosonic string theory to include also fermions into the fold, you naturally end up with a superstring theory. And supersymmetry is a symmetry which also tells us, you can mathematically prove it, that number of bosons in a theory is identically equal to the fermions, number of fermions in the same theory. I would strongly recommend book of my German Guruji, Professor Harald J. W. Müller-Christen. He has written several books on all textbooks. After all, I am his disciple, so he lives in Darmstadt. He was a professor at University of Kaiserslautern, and after his retirement, he lives in Darmstadt, adjacent to Frankfurt. And in each and every visit of mine, I go to meet him. and I spent almost a week with him, going out for lunch and dinner and tea and coffee, essentially to be able to talk to him. So his most famous book is Supersymmetry, where he gives calculational and conceptual details on supersymmetry. That is written on the cover page. Please do look at it. And in the summary of that entire book is that if you talk about supersymmetry, this is a symmetry with a not local, rigid supersymmetry or a global supersymmetry. So it's not local supersymmetry. And that is true of all the supersymmetric field theories. So here I would mention to you a model called as Best-Jumino model, which is the crucial soul of the supersymmetry. So Best-Jumino model has a scalar field, a pseudo-scalar field in its contents, and the spinor field. Now, this applies to all supersymmetric theories. There are two different ways. One is to go these scalar fields and so on. Here we are still talking about zero-dimensional particles and fields. We will gradually go into, because we will need supersymmetry into our string theory. So going to one-dimensional objects. So here this Best-Jumino model talks about a scalar, pseudo-scalar field and a spinor field. Here the masses of all these fields have to be same, and for supersymmetry to be unbroken, and the couplings also have to be identically the same. Whatever interaction terms you have, product of fields, they all will have the same coupling. So this is the unbroken supersymmetry. If you change any of these parameters, then supersymmetry would be broken. And so that is this is one point. And here in general you can have two kinds of formalism. Here in this particular model, which is the soul of the supersymmetry as well as superstring theory, the the supersymmetry is a non-manifest supersymmetry, so you don't see it. When you write the action, you say, oh, okay, there is one Klein-Gordon kind of a field, another Klein-Gordon kind of a field, which is under parity goes as minus pi, goes to minus pi, and spinor field. So what is new about? So you don't see supersymmetry anywhere. The other formalism is called as the superspace formalism, where you explicitly introduce the Grassmann variables into your theory. So you make every field not only a function of x mu but also a function of x mu into theta bar, and your volume element goes from integral d4x to also include integrations over d2 theta and d2 theta bar. So what are their Grassmann variables? And this is called as superspace formalism. And here supersymmetry is visible just by looking at the field, looking at the x, and you say, oh, it's a supersymmetric field theory. So I would not go into the details of this particular theory at the moment. I will come back to the Best-Jumino model with non-manifest supersymmetry. You don't see it anyway. So here the spinor field, if you want to talk in terms of a charged fermionic particles, then you need to have a Dirac spinor. But if you like to have a if you impose a condition that the charge conjugate of the spinor is identically equal to the spinor itself, then you are talking about real. So they are described in terms of Majorana fermions, Majorana spinors. So Majorana particles are the particles that are their own antiparticles. So this is one we also don't need to go too much into it, but only to get ideas from here that how do we construct that. But before coming to Best-Jumino model at all, let me first begin my things with the simple string theory. Okay, bosonic string theory. So that means I am going a step beyond particle physics. So I said the particles and fields we could handle with zero dimensional particles and fields. Now, but in when we talk about zero dimensional particles and fields, we have the uncertainty principle which says delta x is h cross by delta p. And this works for the zero dimensional particles and fields, but I want to include gravity into my theory. So this uncertainty principle would, in the present form, would not be sufficient, would not be enough to take me anywhere. And my divergence problems would remain there, they would not be solved. So what do I want to do? Now, in supergravity theory, I stayed with the uncertainty principle as it was, but I introduced more symmetries, supersymmetry, gauge symmetry, everything to make things finite for us. Okay? So the results have to be finite. You have to be able to make contact with the experimental physics, otherwise it's all useless. Okay? Any complicated theory or mathematics, it's useless if you cannot make contact with observational physics. So now let me propose that I generalize my uncertainty principle to delta x equal to h cross by delta p plus a second term which is alpha prime, some constant which is the famous Rajai slope in hadron physics. So some constant alpha prime times delta p by h cross. And alpha prime is dimensionful. You can, so, and it's actually it goes as the, its square root of alpha prime goes as the Planckian length scale, which is the string length, 10 to the power minus 33 centimeters. Now, in the unmodified uncertainty principle, when delta x goes to 0, delta p can go to infinity. And this led to the divergences in our calculations. Now, if I generalize by uncertainty principle, what would happen? Now, when delta x goes to 0, delta p would no longer go to infinity. Some very large value but finite. Okay? So, some finite value. And therefore, these divergences would not be there. But as a result of this, what would happen? My interaction vertices that I mentioned to you in supergravity theory or conventional field theory or supersymmetric field theory. Now, the interaction vertices would no longer be zero dimensional, but they would be replaced by vertices spread in space-time. So that is the fundamental difference of this approach of string theory with the conventional particle physics of any kind. And as a result of this, what happens? Now the theory, so-called string theory or superstring theory, it becomes super renormalizable. No divergences at all. Because my interaction vertices are no longer zero dimensional. They are spread in space-time. This is the main point. This is the main crux of the matter for going to string theory. And we have included gravity into it by definition. Why? Because now we have these extended vertices in space-time. So you can talk about, if you like, at some later point of time, include gravity and everything into it. There would be no extra problems, no divergences at all. So all those problems would be gone. All right. So how do we go about it? As I said, we should always ask ourselves, how do we go about it? How do we understand it? Yes. Let me consider a one-dimensional string with two open ends. These red are the open ends here. If it propagates into space-time, it sweeps out an imaginary surface which is called as the bird seat. However, if I have a loop, I am sorry I don't have it here, but in every morning you get some newspapers wrapped around in a rubber band. So that rubber band is a loop. So if I oh, I think I have it here. Let me show you in 1 minute. So now this is a loop. If this loop propagates in space-time, this will sweep out an imaginary surface which would be tube, which would be a cylindrical surface, a kind of a tube. So these are the two possible configurations that I can think of, the open string and the, so this is called closed string, this is called an open string. Now, we have to somehow construct the action of our theory which can take care of these modified ideas, and this would probably serve our purpose. So the well-known actions, you see, as I said, classical theories and classical techniques, they are the mother of all theories. So you can consider the action in terms of so you can write down the action of a relativistic point particle. If a point particle moves around in space-time, it traces out a word line. That is what we call a particle, relativistic or non-relativistic. And when a string moves out, it sweeps out a bird seed, called as the bird seed, a surface. And you can appropriately write down the action of these theories. So conventionally or usually, one kind of actions, they involve square root. They are of the type called Nambu-Goto, Born-Infeld-Nambu-Goto, Dirac Born-Infeld-Nambu-Goto, that you can put in many fields into the theory. And another form is called as the Polyakov actions. So they do not involve any square roots. They are a little bit easier to handle. But you, as a curiosity, you can look into both of them. I have studied both of them in my different papers. If you look into, for example, papers on this by anybody, including myself, you can find out there. So all these Nambu-Goto, Dirac, Born-Infeld-Nambu-Goto, and so on, all these actions, they involve a square root. And Polyakov actions, then gauge fix, and so on. And so now what you do, what is important is that for these actions, our classical tricks tell us, classical mechanics, classical field theories tell us, make use of the variational principle, vary the action delta S equal to 0. So using the variational principle, you can derive the equations of motion. So for equations of motion, you will find here, if you have this, one more point is that for the conventional string theory, the bosonic string theory, you have this ambient space-time which is designated by which is spanned by the string field coordinates, which are usually written as capital X mu. So it's a mu dimensional space, and when a particle or a string moves around in this space-time, it sweeps out the imaginary surface. So this imaginary surface can be parameterized by, let us say, sigma alpha, which is a function of space and time, sigma and alpha. So you call it sigma alpha is a function of sigma and tau. So for relativistic point particle, it's just a function of tau. For one dimensional branes, it's, or a string theory, this is sigma alpha is a function of sigma and tau. For 2D branes, you will have sigma 1, sigma 2 and tau. For D3 branes, sigma 1, sigma 2, sigma 3, bird volume. So when a bird seed travels, so this bird seed coordinates sigma alpha, they get embedded into the space-time manifold. So X string coordinates are now functions of, in field theory they were functions of X mu. So they are now functions of sigma. Instead of mu, I cannot use mu many times. So capital X mu, the string coordinates are functions of sigma alpha. This would hold true for the bosonic strings. If I have superstrings, I will also have to include Fermi fields into my theory, and they would, let me call it capital psi mu. So they would also be mu dimensional in the space-time manifold. They would also be functions of the string coordinate, the bird seed coordinates. So string fields are functions of bird seed coordinates. So capital X mu and capital psi mu, they are functions of the bird seed coordinates sigma and tau. So this is what your basic framework of a string theory. Now you make use of the variational principle, you derive the equations of motion. What are you going to get? You are going to get the equations of motion. So equations of motion would be of the type, let us say the Klein-Gordon type, Klein-Gordon equation. And if you have also Fermi fields in your action, then you would also have Dirac equations for this. So these will be the equations of motion. Now we know from non-relativistic mechanics that the solution of a wave equation you can always split into the left moving waves and right moving waves. Whenever you need, you can split them into left moving and right moving waves. So in string theory, they are called left movers and right movers, just conventional. You can call them anything. So you get you can split x mu and capital X mu and capital psi mu, which are string field coordinates, into the left movers and right movers. Okay, so left movers and right movers, function of if a simple wave in simple mechanics, f, you write the differential equation for f or the wave equation, so it will be f of vt minus x and vt plus x, f of vt plus x, so moving left and right. Now in string theory you can do the same thing. You can, after having studied your different actions, obtaining their equations of motion using variational principles, now you can, wherever needed, for example for closed string, you have to have definitely left movers and right movers going clockwise and anti-clockwise. Now you also look into the theory of partial differential equations, and the solutions of partial differential equations can always be expressed as Fourier expansions. That is what we did in one-dimensional harmonic oscillator in quantum mechanics. That is what we can do, or we did, for scalar field, vector field, spinor field in conventional field theory. And the same thing we would need to do also in the string theory. So in string theory also we would need to make Fourier expansions. They are called Fock space decompositions even here and even there. Fock space is a space where the diagonal elements are non-zero and non-diagonal elements are zero. So take example, the best thing to learn all these things, master all these things for me has always been done one-dimensional harmonic oscillator. If you look into my video lectures on string theory or on superstring theory on my YouTube channel, as I said, you can locate my YouTube channel by writing my full name. So there are many lectures which I gave at the University of Oldenburg. In my early days when I taught, there were no possibility of video lectures. So it was a loss to the younger generation. So here you can find that, so I always start, whether it's superstring theory, I always start with one-dimensional harmonic oscillator, construct things, states, as I said, n particle states going back to vacuum state and so on, using one-dimensional harmonic oscillator, then apply it and extend it to simple scalar field theory. So here the annihilation and creation operators are still simpler, but if you would talk about vector field like electromagnetic field, then you will have to introduce polarizations. If you want to talk about spinor field, of course the annihilation creation operators are independent of that, but as coefficients you would also have the spinors in Dirac spinor field, for example, or vector field. So but they are very doable things, and I would recommend simple books like Louis Ryder and Mendel, and so they are the simplest books. And of course, my great friend Ashok Das, his lectures notes on quantum field theory, and his lecture notes on um, uh, field theory from path integral approach to field theory. It's very, very famous. Path integral. He is a professor at Rochester University, and one of the simplest guy. Very, very knowledgeable. To talk to him all Vedas, Upanishads, whatever you like. You can invite him to your place when he to your institutes, and he is a simple person. Very, very simple. Very rich in knowledge. You see. He comes from a place called Bhadrak in Orissa. Very, very great soul, very rich in knowledge. So, you see, you talk about the creation and annihilation operators, you talk about the scalar field, vector field, spinor field, you talk about this, and then you also say always that okay, we make Fock space decomposition, which means by construction we generate our Vishnu, the preserver, a dagger times a, to be a diagonal matrix. Okay, non-diagonal components are zero. That is the beauty about it. So you can also make Fock space not just on par with field theory, Fock space decompositions for scalar, vector, and spinor field. Now you do it for string fields. So the bosonic string fields as well as the fermionic string fields. Okay, and you have to obey the laws of simple laws of physics which go by common sense, like so the creation and annihilation operators in fermionic case, they would have to obey anti-commutation relations. Okay, and so you can read from Mendel, and so you can read from Ashok Das. Things are very beautifully explained, but even in my video lectures I have explained these things sufficiently well. Any person with a simple master's degree or even undergraduate degree can follow my lectures. So don't throw them away, but just by the name, oh, superstring, it is too difficult, I leave it. No, everything is simple. You have to do it. If you read, it's simple. Okay, everything is doable. Otherwise, why would anybody else do? If they were undoable, and then if DSK can do it, you can too do it. You too can do it, but even better than me. You see? So that is the idea. So here, and then you construct the mass spectrum of the theory exactly the same way that you do in field theory, that you do in one-dimensional harmonic oscillator in quantum mechanics. You do the same thing with a scalar field, vector field, spinor field in field theory, in a four-dimensional field theory. Now you have to do the same algebra, same techniques used in string field theory. Now, what happens, the results are very encouraging, very beautiful. You see, I am working within the framework of concluding my talk in 1 hour or so. So, you see here, the different particles are different vibrational modes of a string. That is what you have to, this creation and operation, creation and annihilation operators that you now talk in string theory, they talk exactly about this. They give you a handle on all these things. So now, you consider the different vibrational modes of a string. So they are just like different musical notes. Sa, re, ga, ma, pa, dha, ni, sa. And the string is like a stretched string, okay, like that of a guitar string or a violin string, okay. Things are not doable because mathematics, I am telling you, in a very simple manner. The concepts are rich, but they can be understood through simple mathematics. Those who want to learn a little bit further are encouraged to go to my video lectures one by one slowly, and you will find, oh, whatever I was talking here, it is same thing there. And then because I have more time, in Germany there is a culture of 2 hours teaching per class, 2 hours teaching, so 90 minutes, concrete teaching for 90 minutes. So my each lecture goes over 90 plus minutes. I usually take few more minutes, so it goes from 90 to 100 minutes. Okay. So and then too many lectures, so you can do things a little bit slowly. Here I am giving you a summary and overview of what you can do, what is string theory, what you can do. And this is the, I personally, being a teacher, I'm more of a teacher, so I tell you practical steps. I'm a simple small guy where people talk many big great things, but I tell you the tricks, techniques of learning it, how to learn it, how to do it, how to go about it. This is what you will find in my all my talks. I tell how to do it. Classroom teaching I love to do and love to teach. So you can construct the mass spectrum of these theories: bosonic string theory, fermionic string theory, or the superstring theory, where you have bosons as well as fermions. And so you can calculate the mass operators. It actually goes over several lectures, but the concluding result would be the mass squared operator when applied to a state, what you obtain, the mass spectrum. For a open string theory, the ground state is a tachyonic state. What is a tachyonic state? Here mass squared operator is negative, so the mass is imaginary. Such a state is called as a tachyonic state. So ground state of a open string theory is tachyonic. Actually, the same also holds to the ground state of a closed string. Okay, a closed string also, the ground state is a tachyonic state with mass squared operator as negative mass squared operator. So this is one thing, but the first excited state in open string theory is a vector-like state, which means a photon-like state. Vector particle is a photon. Photon is a vector particle. Okay, so a photon-like state, the first excited state of a open string theory. What about the first excited states of a closed string theory? The first excited state is tachyonic, so it's unphysical. Okay, unphysical with negative mass squared or imaginary mass. But the first excited state of a closed string is a tensor state. What is a tensor state? G mu. This is graviton state. So the ground state of your the first excited state of your string theory, of your closed string theory is contains, the first excited state contains a graviton with a spin +2, and it also contains an antisymmetric two-form gauge field called B alpha beta, or by whatever name you like to call it, but antisymmetric two-form gauge field, and you have a scalar dilaton field. So these are the three things that you get in the simple. You can even obtain it qualitatively. You don't have to go to the quantitative estimates. You can go to qualitative things. You will find that these things you encounter in the mass spectrum of the open and closed string theory. Now, in the fermionic string or the superstring, you also have Fermi fields. And the way I might take a couple of minutes to tell you how to introduce that thing. So coming back to the so-called Best-Jumino model, if I drop my pseudo-scalar field, I just have a scalar field, and I replace that scalar field with capital of X mu, the string coordinates, bosonic string coordinates. So that would be my first term. You see 1/2 d mu phi. So phi replace phi by capital of X mu, the string coordinates. X mu in turn is a function of sigma alpha, sigma and tau. Okay, so you are working in string theory. And plus an additional term which is capital of psi mu, which are fermionic coordinates. They are psi of mu. They are also functions of sigma and tau. Now, while doing string theory, so replace the Grassmann, the spinor field in your Best-Jumino model by this. If you look at this book of my friend Professor Harald Müller-Christian, he has devoted several chapters and pages on the Best-Jumino model, which you can learn all different things, taking example of Best-Jumino model, also constructing it in superspace and superfield formalism, also staying in the conventional approach where the supersymmetry is non-manifest. You see, for discovering these things in string theory, it took decades. And those people, one of them is a great friend of mine in École Polytechnique. No, School Superior in, I'm forgetting, Gervais, Monsieur Gervais. He has been to India. I took him to show him Bittur, the Ganges from IIT Kanpur, long ago, with some very, very well-known other scientists. Veneziano and other people were there. So I was too young at that time. They told me, Kulshreshtha, why don't you take these guys to show Bittur in Kanpur? So he invited me to his École Normale Supérieure. Yes, École Normale Supérieure. I was there once on when you go from Champs-Élysées to Jardin du Luxembourg, you can walk, and on one side you come across this École Normale Supérieure. And Mr. Gervais and Sakita, they found these supersymmetric transformations of this string theory. They are famous for that, and Gelfand, or what, I have forgotten another name, very famous name, who independently discovered these transformations. But you also, later on I learned that they were also discovered, they were perhaps known much earlier in the context of Best-Jumino model. So these are, and here in the context of Best-Jumino model, the same thing also for string theory, superstring theory. The transformation parameter is a constant Grassmann variable. It's not a field, because it's not local symmetry. It's rigid supersymmetry or global supersymmetry. So here, now after you include supersymmetry into the theory and the fermions, automatically you come across supersymmetry. You cannot do it without that. So now you again find the mass spectrum of the theory. Then in superstring theory, there are two ways of taking the boundary, implementing the boundary conditions. One of them is called as the Raymond sector, and one of them is called as the Nebuchadnezzar sector. So mass spectrum, when you obtain of a superstring theory, in the Raymond sector, you come across space-time fermions, okay, like electrons and quarks and so on. But when you do Nebuchadnezzar sector, you end up with the mass spectrum in the bosonic space-time. So Raymond sector gives you mass spectrum in the fermion sector, space-time fermions. You end up with space-time fermions, and in Nebuchadnezzar sector you end up with space-time bosons. So the mass spectrum is very rich, and in fact, if you look into more of these papers, there are many experts. Even in India, Ashok Sen is the well-known name for, he is known by the name of string theory or superstring theory. Nobody can beat him till date. And Sunil Mukhi, also a great friend of mine, at Tata Institute now, he has, I think, shifted to Pune. He's a great speaker, he's a great teacher. Now Ashok Sen has also developed into a great teacher. Originally he was, Sunil Mukhi was always leading the teaching part, a very vocal, versatile man. So I would recommend you to look at some of the work of these guys, Ashok Sen and Sunil Mukhi. There used to be one friend of mine, He is there in Bhubaneswar, Gyan Maharana. Very knowledgeable and very good teacher. And I personally learned many things from Gyan Maharana from Bhubaneswar. And now, well, of course, there are many, many more theorists who would tell you much more than what I know. They do hardcore physics. I no longer do that much hard work. So I'm only doing soft work, if you like to call it soft work. I cannot do that much hard work now anymore. So I do soft work like talking to you people or talking to my students. So the here you can obtain all these mass spectrum of the string theory, different vibrational states. They correspond to distinct particles, okay, and you can characterize them by different quantum numbers like spin, mass, and so on. And I think lot of progress has been done. I can't even summarize it into this lecture, but you please have a look into the achievements of many of our own Indian people in this field. You don't have to worry too much. We have many leading theorists, string theorists in our country, many leading field theorists in our country. You look into that and you will know many more. But so making contact with experimental observational physics is now the main challenge before the string theorists, because you started off with one-dimensional objects, open or closed string, and now but you have to eventually face the experiments, the observational physics, and therefore you have to make certain reductions from going to, because consistent bosonic string theories are defined in D equal to 26 dimensions, and consistent superstring theories are defined in D equal to 10 dimensions. You see, because of the different requirements of central charge has to be zero and no ghost condition and so on and so forth. So these are you have to work within those limits, and then you can obtain meaningful mass spectrum by the present times. We have already made lot of progress, and then some other people. There is one guy, my great friend Samir Mathur at Ohio State University. His expertise is in gravity and string theory and black hole physics, and he is the one who is credited with solving the black hole information paradox. The information, the black holes, they also die away eventually. They are not eternal. So the information in the radiation, thermal radiation, might get lost, and then we would end up that losing the information as to what once made a black hole. So you look into the work of Samir Mathur of obtaining, resolving this paradox within the framework of string theory, and he comes to India very often. His parents, I think now may not be there. I have met his father a couple of times, but he comes and lives in New Delhi. His sister lives here, so he is a frequent visitor to India and also to Delhi for family reasons, and for he has given several. All these guys, they have given several talks in our Department of Physics and Astrophysics, Delhi University, and so there are lots of achievements. I mean, mainly also from our own Indian people, and so black hole physics within the string theory, you are able to solve many black hole information paradox, thermodynamics of black holes, and many other things. So one can achieve all these things, and I can see that I have been speaking for 65 minutes now, so I gradually conclude. So you see, this is bottom up approach and bottom down approach. You can go from conventional field theory to supergravity theory to superstring theory, and this is one way string going up, and further is beginning from string or superstring theory, you come down to supergravity theory, you come down to conventional standard model physics. To make the aim is the same. You try to make contact with the observational physics, with the experimental physics, how best you can do, in what method, what approach, which ladders you are supposed to take, you have to carefully decide, but have an overview on both the sides, going from this way to this way and going from this way to this way. So remember that string theory holds true at the Planckian scales, where mass is 10 to the power 19 GeV. The length scale is 10 to the power minus 33 centimeter. The time scale is 10 to the power minus 43 to minus 44 seconds, and so on. And conventional standard model holds true at the conventional energy that one of you just mentioned, the experiment at CERN. So, they are accessible energies at the moment for us, what we can practically do. So, these are the things. So, either you have to extend in your superstring, in your supergravity theory, you have to somehow extend the zero-dimensional vertices to vertices spread in space-time, like in string theory. Or in string theory, you have to make the reductions from high energy to low energy side. Okay, so the idea is to meet the experiment somehow and make sense out of whatever we are trying to do. But we have many brave souls also in our country, and not to talk of the whole world, but also around the whole globe. So a lot of new physics has come out. In black hole thermodynamics, a lot of things have been explained by string theory. Similarly, many things have been resolved. I would not be even able to count them. So, but for me as a teacher, I find it a beautiful approach. What is the harm? I can develop field theory of zero-dimensional particles and fields. I can develop field theory of one-dimensional objects. I can go from here to there or from there to here. And the mathematics is doable and very simple. Anybody who has little more interest, please do look. But because in my video lectures, I also always recap simple things of quantum mechanics, classical mechanics, their correspondence, and the simple examples in quantum field theory. When I gave, 2.5 decades I taught field theory 1 and field theory 2 in Delhi University. But unfortunately, those lectures and talks were not recorded. The last course that I gave was on quantum mechanics, that some students recorded, and they are now available on my YouTube channel. So after that, in the last few years, I became little bit conscious about it, that after all, younger generation, they do look at you. So if you look into my YouTube channel, they are 1,500 subscribers, and the more views, something like 60,000 views of all these different lectures. And I might advertise one more lecture of mine that I gave 1 year ago on the TED platform or TEDx platform. That is looking for a theory of quantum gravity. It's a 19 minutes talk. You might, for that, it's not on my YouTube channel. You have to write separately my name and TDX or TDX or TEDx or something. So you will not be bored, because it's only a 19 minutes talk where I summarize some of these thoughts that we have been talking in the last 2 hours. And but I always talk about simple things. Also in my classroom teaching, I do step by step. If you look into my lectures, you will find that I give each and every step. I prefer chalk and talk method. Today I am not using chalk and talk method because I have no such arrangement at my home, and I am not showing you slides, because then it's too much work for writing all these things, collecting in a particular order, then the ordering keeps changing every day. So I depend more on my brains, and I am dictated continuously when I speak to you. In my conversation, I am always dictated with my... Actually, I minimized looking at slides and so on long ago. because earlier, but I was showing a few slides, but I found that it was much easier to rely on the brains rather than the other platforms. So I offer my apologies to you for being for not being able to tell you many things and show you some equations, or there are no diagrams. Well, if I get a time at some point of time with some of you or all of you, then I would have shown you in my supergravity understanding, I could show you several Feynman diagrams, like if you can consider the bending of sunlight, okay, under gravity. So sunlight means, so if you look into my, and I always relate things with classroom teaching. Look at the book by Mendel and so it's like a Bible. It's not so easy, but you learn it, and then it's very simple. So there somewhere in chapter 8 or something, it talks about this classical photon coming out of a nucleus, and it interacts with a electron or a photon, and they give you some observable thing that is called Bremsstrahlung, I suppose. So in gravity theory, supergravity theory, sunlight is coming. So what is sunlight? Sunlight is, my photon is coming from the sun, okay, which means from some nucleus, okay, for me. So it's a classical photon, and it can interact with a gluon. Gluon couples with everything. So it can interact with gluon, then the gluon is propagating, it absorbs a classical photon coming from the sun, and then this gluon can split into a pair of two photons, or it can split into a pair of electron positron, which can combine maybe at two different places. So at one end you get a one loop, quantum corrections to this process. See, so the quantum corrections to various processes, they are measurable. They are, they are calculable, but their net amount is very tiny. So the point is, they are doable, they are correct, but how to go to these experiments which can detect these small transition amplitudes, these small transition, because if the graviton is involved or gravity is involved, the transitions amplitude cannot be comparable to that of strong interaction processes and so on. But my message is, most of the things are doable, are calculable. The contribution, net result of the transition amplitudes is too tiny, and making contact with experiment becomes too difficult. So here you can do these calculations also, including gravity, and so on. Well, in my video lectures, perhaps there is one talk which I gave 1 year or 2 years, in the last 1 or 2 years, where my friend Sten Brodsky was also. There is a series of seminars, London Oldenburg seminar series. I gave one talk on supergravity in that, and because some people, when asked about making contacts with supersymmetry, Sten himself was available to explain how to make contact with supersymmetry in the hadron physics, which is of course experimental physics, doable in the lab. Okay, and I remember when at the time of my talk, it was very early in the morning, at 6 o'clock in Palo Alto, where he lives in California. But for a friend like Daya Shankar, he calls me Daya. He got up, he was, after his shower and so on, he was sitting fresh at 6 o'clock of Palo Alto to listen my talk on supergravity. So I think, let me express my heartfelt thanks to all of you for tolerating me for these more than 2 hours now in my 2 talks. And I apologize for many of my shortcomings I may have made, because I'm not looking at any slides, or except that I looked at my Sanskrit shlokas, because I didn't want to convey you wrong things. So for making sure that I spoke correctly, so But please do look into, don't ignore them. Don't look at, my father told me while I was a small child, don't look at Ramayana and Gita as religious books. So I have a small book on this. It's lying on my desk all the time in books. I don't care whether I have taken bath or whatever. No, this is not a thing of puja, hath jodna. Nahi. It's a thing you need to read to understand. The same applies for me also to Ramcharitmanas. I tried many times learning from Valmiki, Maharshi Valmiki, and it's very heavy books, 2 volumes, and but it's Sanskrit and Hindi translation because my Sanskrit is very poor, but I make efforts, and I would encourage all of you to do that. You see, Sanskrit is a very rich language, and as the people say, Deva Bhasa, ये देव भाषा है, देवताओं की भाषा है, माने एंशियंट लैंग्वेज है. देखो, so we should not abandon it. If a Western person tells us this is correct, then we say, oh yeah, we were fools, we didn't know this. No, you look into your thing. Aryabhatta, Brahmagupta, they were great people we had. All these, they have discovered many things. They have written many things. We need to learn. So with that, I express my thanks to all of you once again. And I leave the platform to the organizers. If you still like, you have energy to ask. I'm full of energy, as you can see on my face. When I talk,
on behalf of all the participants, I really thank you for such a profound, such an interesting and motivating lecture. So like I told you, I'm a social scientist. But
great.
For the past half an hour, I've been reading up on my phone about superstring theory and
my goodness.
I was so fascinated. I have studied physics only till class 12, but I've been reading about supersymmetry for the past half an hour. So that is how motivating you are, sir.
Divyaji, I'm thoroughly impressed and thoroughly inspired by these statements that you were looking at.
And I'm just resolving that I'm going to hear your TEDx talk today evening so that I can learn something about what you were saying. So we really are very grateful to you.
I think that's a good compliment to me, that if people, social scientists also get some motivation. I can imagine 80 people, they are very simple people. Usually, Divyaji, in our physics stream and in general in science stream, people are very simple and humble people. It's not that they do not know, they know a lot, but they are very simple, they are very modest people.
Yes, sir. Scientists always are.
And I'm very sure many of them must be feeling excited and thrilled. And for that reason, I like to tell the basic references. I again repeat in 1 minute. Please look at my video lectures on various things, whatever is available there. I have to upload many more that are with me on my YouTube channel. And look at the basic book, for example, Supersymmetry book by Harald Müller-Kirsten. You will also look into his textbooks on classical mechanics, quantum mechanics, 1000-page quantum mechanics. When 550 copies somebody booked from America, he was so excited, he wrote me the mail. Oh, Professor Kulshreshtha, can you believe it? In one go, they order 550 copies of my book. I said, you have written each and every step there. So look into his classical quantum electrodynamics book is extremely good. Many people do not know how to calculate the matrix. In your Lorentz transformation in first year we read in the component form. So 4 equations. X goes to x prime equal to so and so, y prime, z prime, t prime. But when you write them in the covariant form, x mu goes to x prime mu equal to a mu nu times x nu. And he tells exactly that this matrix can be calculated in terms of a simple matrix involving partial derivatives of primed with unprimed coordinates. One of them for relativistic and one of them for, stationary framework. So even a great book like David Jackson, I visited him once, he invited me to Berkeley. He also simply says, now we can simply guess that this matrix will be this. And many of people teach it like that. I tell them, no, there is no jantar mantar, you just, no, everything has to come out of some mathematics. The concepts have to be related to mathematics. Mathematics has to be related to concepts. Otherwise, the beauty would be lost. And so this is what I spend my lifetime trying to do, these little things, marrying concepts with mathematics and mathematics with concept. This is one of my.
Thank you so much, sir. Thank you. We are really motivated,
thank you,
and
thank
I'm
you.
impressed. They are all motivated, I hope,
No.
to follow in your footsteps and dedicate themselves to this kind of science and to teaching science well. So thank you, Professor Kulshreshtha, and we are indeed blessed that you were here with us today.
I'm thoroughly grateful to you. I'm thoroughly excited and impressed and inspired with the interest that I have already seen, and I suppose we still meet on Friday.
Yes, sir.
Afternoon.
Yes, sir. We meet again, sir. We're going to meet again, sir, and we look forward to it. So we wish you a very good evening. Take care, sir. All our good wishes and regards, sir.
Okay.
Namaskar, sir, and bye-bye. Bye-bye,
My
sir.
lots of
Bye-bye,
love
sir.
to all of you. My lots of thanks
Bye-bye,
and
sir.
love to all of you.
Thank you.
Thank you so much. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you very much.
Thank you.
So with this,
Thank
we
you, sir.
conclude today's
Conclude.
proceedings. We are ending today's session. Now you will please be ending for the day. We'll meet again tomorrow morning at 10:05, 5 minutes past 10. Please be
Thank you, sir.
punctual. Again, I'm reminding you about being punctual. That is all. Please, we'll meet again. Tomorrow's-
Divyaji, I would be very grateful to you if you could send me a list of the email addresses or contact addresses of these participants, whatever is available
Yes,
with
sir.
you. Because
Yes, sir, I will send it. I will send
I
it to
also
you,
have
sir.
a curiosity to know the persons with whom I have been talking. So
Yes, sir. I will do that, sir. I
Okay,
will
thank
send
you,
a
thank you,
profile
thank you.
of the group.
My
I'll do that.
Gmail is very simple, dayashankar.kulshreshtha@gmail.com. All
All
small
right, sir.
letters.
Yes, sir. I will be
Dayashankar.kulshreshtha.
sending it, sir. I
Thank
will
you
be
so
sending
much.
it, sir.
Thank you so
Bye
much.
bye, sir. Thank you,
Bye-bye.
sir.
Bye-bye.
So, participants, bye bye. Take care. We'll meet again tomorrow morning, 10:05. All right. And we will share tomorrow's schedule on your WhatsApp group. And the day officer tomorrow, I think we have, let me just check. Tomorrow we have Manjulata Yadav as the day officer. And tomorrow Amit Uke will be writing tomorrow's report. आज की रिपोर्ट अमनदीप सिंह जी ने लिखनी थी. Amandeep, you have to write today's report and please submit it all in the WhatsApp group. तो अमनदीप जी आपने आज की रिपोर्ट लिखनी है. कल सवेरे तक आप इसको सबमिट करेंगे. Tomorrow, Manjulata, you are the day officer and Amit Uke is the rapporteur tomorrow. So with this, bye-bye.
Divyaji, if you do not mind, please include my phone number in your WhatsApp group.
I'll do that, sir. Definitely, sir.
Okay. Thank you.
Yes, I will do that, sir. We'll make you
Just
part
for
of the
my
group. It will be a
curiosity
privilege.
purposes. Thank you.
Yes, sir. Thank you, sir. Namaskar, sir.
Namaskar.
So, bye-bye.
Bye-bye.
Thank you.